Right, so this is going to be a big video covering RAT6 through 8. So we're going to start off by talking about a certain kind of rational function. Now, rational function, remember it has the word ratio in it. That means we're talking about a fraction. And the basic rational functions look like this, where it has some number in the numerator, and then x, then plus or minus something in the denominator, plus a number on the end, which we'll call k. Okay, so this is a over x minus h plus k. Now you might already recognize a, h, and k from Unit 3. These are very similar a, h, and k's to that. They mean the same thing. All right, so our first example is 3 over x plus 2. Now, 3 over x plus 2 cannot have an x value of 2. Or, sorry, negative 2. It cannot have an x value of negative 2. Why not? Because if we plug in negative 2 here, we get negative 2 plus 2 in the denominator, and that is, of course, 0, and we cannot divide by 0. So x cannot be equal to negative 2, and there's a phenomenon that happens here. All right, we actually can draw a vertical line at negative 2. So like, let's say this is negative 2. We can draw a vertical line here, and this is actually called a vertical asymptote. And what this means is that the graph cannot touch this line. The graph cannot touch this line. Now, there is also what we call a horizontal asymptote, and that is at whatever the value of k is. So in this case, we keep in mind plus k is at the very end. In this case, we don't have a k value here, so this is effectively the same as plus 0, which means our horizontal asymptote is at 0. So we have a vertical asymptote and a horizontal asymptote, and the graph can't touch either of these lines, but it can get very, very close. It can get very, very close to these lines, and that's what it in fact does. So the graph is this kind of like swooping arc shape. I like to call it a swoop. The formal term for it is a hyperbola, and it's in the top right corner, and it's also in the bottom left corner. Now, if you're sketching this, it is kind of important to note that both of the arcs curve at the same steepness. So both of the arcs have the same kind of steep arc here. All right? So if I turn it this way, you'll see it looks very symmetrical if I turn it 45 degrees. That's normal. So this is called a hyperbola. It's also called a swoop. And we can say a few things about this hyperbola. First of all, the parent function of this is y equals 1 over x, which has vertical asymptotes at 0 and 0, and it looks like that. So if we were to describe the transformations of this function away from its parent, we'll say that it's shifted left because the vertical asymptote is no longer in the middle. The horizontal asymptote is still on the x-axis, but the vertical asymptote is on the y-axis, so it's shifted left. It's not shifted up or down any because the horizontal asymptote is still at the x-axis. So for transformations, we can tell which way it's shifted by where the asymptotes are. Additionally, we can say that the hyperbola has been stretched by a factor of 3, because that is what the numerator is. So the stretch factor is still a. Remember, a controls dilations and reflections, and our a in this case is positive 3, so that is in fact a stretch, because it is bigger than 1. Okay, now we have to talk about domain and range. The value that we can't include for the domain is x equals negative 2, because there's a vertical asymptote there, and if we plug in negative 2, we get 0 in the denominator, which is bad. So our interval notation should include every value except negative 2, which we can write like this. Where the first part, again, these are all parentheses. The first part is everything from negative infinity up until negative 2, so every value up until negative 2, and every value from negative 2 onward, but not including negative 2 itself. That's why the parentheses are here. Now the range we can do the same way, but this time the y value that we can't include is 0 because that's where the horizontal asymptote is, and the graph cannot touch that y value. Okay. Now for the next one. All right, we have, once again, a rational function. This time, the value of x that we cannot plug in is positive 5. So we have a vertical asymptote at positive 5. Let's just say it's here. And k is positive 3, so that's going to move our horizontal asymptote up to positive 3. Now in this case, our a is negative, which is going to cause a reflection. So it's going to cause a reflection, and because of that, the parent function is going to flip upside down. And instead of the hyperbola existing in the top right and the bottom left, it's now going to exist in the top left and bottom right. And that's only because a reflection has taken place. Again, this is only because a is negative. This numerator is negative, and that's what causes the hyperbola to flip. We can also say that it is stretched by a factor of 4, because that is what the numerator is. We disregard the negative when we talk about stretches and compressions because the negative only determines a reflection. And it's shifted away from the center. It's shifted this way and this way. Right? It's shifted over here. So it's moved this way. It's moved to the right, which we can abbreviate with an arrow. It's moved to the right. How many? It's moved to the right 5. It's moved up. How many? It's moved up 3. All right. The domain, the value of x that we can't include. That's what we can't include in our interval notation. That is 5 here. Again, if there's a part of this that you're not understanding, don't copy it down. Rewind the video until you understand it, or come to me with the question next time you see me, or email me. All right. Range, we can't include the value of positive 3 because that's k, that's where our horizontal asymptote is. All right, next we have 3 over x. The value of x that we cannot plug in is 0 this time. All right. Our vertical asymptote is therefore right down the middle. And our horizontal asymptote is at -1. Because that's what k is. K is -1, so therefore our horizontal asymptote is at -1. Now, the numerator is positive, so there's no reflection. Instead, we just have a stretch by a factor of 3. It doesn't really matter, as you can see, it doesn't really matter what order we list the transformations as long as we list all of them. And it is shifted because the horizontal asymptote moved. So which way did it shift? Well, it shifted down, right? Because it started in the middle, and then it shifts down 1. All right, the domain and the range. We can't include the value of 0. And we can't include the value of -1 in the y. Oop, that should be -1. There we go. Okay. For the last one, where this denominator is equal to 0, we actually have to kind of solve it out here. So if we solve this out, we get x equals -5 over 2. And again, I set this equal to 0 and then solve for x, so we know that this is actually the value of our horizontal asymptote. So therefore, this is our excluded value. -5 over 2 is the same as -2.5, so it's over here. All right. And our horizontal asymptote, well, we have a +0 on the end here, effectively, so it's right in the middle still. And the numerator is positive, so we're going to get a swoop that looks like this in the top right and the bottom left. That's what I forgot to include over here. Top right, bottom left. Because again, the numerator is positive, there's no reflection, so top right, bottom left. As for which way it has, or as for how much it is stretched, that's the numerator. So it stretches by a factor of 7. It has shifted left by 5/2. The domain cannot include the x value of negative 5/2. And the range cannot include 0. Okay, so now what I want everyone to do is take 8 minutes, or I gave everyone in class 8 minutes to do K, L, and M. Now I'm going to pause the video, and I'm going to give you a countdown to when it will resume. Alright, so make sure that you have done these problems, or make sure that you pause the video and that you have done these problems by the time I resume. Alright, it's okay if you make a mistake. It is okay if you make a mistake, just fix it once this resumes. If you have no idea where to start, you need to stop the video here and email me. This will not help you at all. This will not help you at all if you don't know where to start from here. Alright. 3, 2, 1. Alright, so this is what you should have. This is what you should have. Alright, this first one, top right, bottom left, because the numerator is positive. This is where it's shifted, this is where it's stretched, that's the domain, and that's the range. Alright, this is the second one. And this is the third one. Note that because there's nothing in the denominator with the x, the excluded value, remember, is x is not equal to 0. And that's why the vertical asymptote is here. And there's a plus 0 at the end here, so k is 0, which is why the horizontal asymptote is here. Okay, I am now going to move to RAT7. Okay, so this is RAT7. We're going to continue with rational functions, but this time we're not going to be talking about the same kind of rational functions. We're instead going to be talking about general rational functions which have a numerator function divided by a denominator function. Now, there are some rules here. Vertical asymptotes work the same as usual. This is wherever the denominator is equal to 0. In this case, we have a function in the denominator, so wherever that equals 0, that causes a vertical asymptote. Now, there are 3 rules with horizontal asymptotes, and it depends on the degree of the function. So, remember degree. Degree means the highest exponent. So in this case, we have a degree of 3 on top because it's x cubed, and a degree of 1 on the bottom because x has an exponent of 1 and 1 has an exponent of 0. So therefore, x has the highest exponent, which is 1. So the degree of this whole thing, x minus 1, is 1. Now, this all depends on the degree. So if the degree of the numerator is bigger than the degree of the denominator, then the horizontal asymptote does not exist. If the degree of the numerator is equal to the degree of the denominator, you divide the leading coefficients, and if the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is at y equals 0. It's at the x-axis. So let's put this into practice. For the first one, we have a cubic over a linear. So the cubic has a degree of 3, the linear has a degree of 1. So because the cubic has a degree of 3 and the linear has a degree of 1, the cubic has the higher degree. Because the numerator has a degree that's higher than the denominator's degree, the horizontal asymptote does not exist. So, again, here's the directions. It says sketch the asymptotes. Only the asymptotes. So now we just have to find the vertical asymptote. The vertical asymptote is wherever this denominator equals 0. So where does x minus 1 equal 0? Well, if x minus 1 equals 0, then x is equal to positive 1. So therefore, x cannot equal positive 1, which makes sense. If we plug in 1 here, we get 1 minus 1. That's 0 in the denominator. That's bad. And we get a vertical asymptote here. Now, all this problem said to do was sketch the asymptotes, so we are actually done here. This function actually looks a little bit weird, which is why I'm not sketching it now. All right, g of x. On the top here we have x plus 1, which is linear. On the bottom we have x squared minus x minus 6, which is a quadratic. So we have a linear on top with a degree of 1, and a quadratic on the bottom with a degree of 2. So the horizontal asymptote, if the degree of the numerator is smaller than the degree of the denominator, the horizontal asymptote is at 0. Yeah, I'm just going to write that real quick. The vertical asymptote depends on where this is equal to 0. So this, real quick, factors into x minus 3 and x plus 2, which means that if we were to try to set this whole thing equal to 0, we'd have division into cases. So we'd have x minus 3 equals 0 for the first case, which gives us x equals 3, and x plus 2 equals 0 for the second case, which gives us x equals negative 2. So the vertical asymptote is at negative 2, and another one at positive 3. We can have multiple vertical asymptotes, but there is only one horizontal asymptote. Negative 2 and positive 3. All right, for this next one, this numerator does factor, but do we need to factor it? No, because all we're worried about right now is the asymptotes. So all we're really worried about is the degree of the top, the degree of the bottom, and what this denominator factors into. What the denominator factors into so that we can figure out where it's equal to 0. What x values would make it equal 0. All right, so for the horizontal asymptote, we're going to look at the degree. We have a quadratic and a quadratic. Those both have a degree of 2. So because these have a degree of 2, we're going to look up here. If the degree of the numerator is equal to the degree of the denominator, we divide the leading coefficients. So 2 over 4. 2 over 4 is equal to what? Say it's equal to 1 over 2. You need to know that at this point in the year, you need to know that 2 over 4 is equal to 1 over 2. We've done simplifying fractions enough. All right. That's going to be a horizontal asymptote at 1/2. Okay, this right here factors using greatest common factor into x times 4x plus 3. So because of this, we have two cases, one where x equals 0, and one where 4x plus 3 equals 0. And if we solve this latter one, we get x equals negative 3 over 4. So the vertical asymptotes, I'm going to write it down here this time, are at x equals 0 and negative 3/4, which is right here and right here. Okay, so that's the idea. For the next part is point discontinuities. Point discontinuities are also called holes. H-O-L-E-S, holes. All right, this is where the numerator comes into play. Because there are places where the denominator equals 0, where the numerator also equals 0, and that causes some issues. So this numerator factors into x minus 4 and x plus 4 using difference of squares. All right, this denominator factors into 2x minus 1 and x minus 4 using a cross puzzle. So because of this, we have a common factor in the numerator and the denominator, which cancels out. Okay, and because it cancels out, this causes a point discontinuity. Whereas the 2x minus 1 being in the denominator causes a vertical asymptote. So if it cancels out, it causes a point discontinuity, whereas if it doesn't, it causes a vertical asymptote. So the vertical asymptote is where the denominator equals 0 uncancelled. So 2x minus 1 equals 0. That's going to be at positive 1/2. All right. This part's, I'm going to admit, it's not going to be drawn to scale. All right. The horizontal asymptote, and again, we don't include 4 here because 4 is where it is equal to 0 but canceled out. This causes a point discontinuity, not a vertical asymptote. Okay, horizontal asymptote uses the degree. So the degree of the numerator, this is a quadratic, over a quadratic. They both have a degree of 2, so we're going to divide the leading coefficients. Again, this is 1 in front of the x squared, but we don't need to write that. 1 over 2. That's our horizontal asymptote. And our point discontinuity is going to be over here at x equals 4, because that is where the denominator is equal to 0, but it cancels out, where both the denominator and the numerator are equal to 0. That's what causes a point discontinuity. Okay, so I'm going to draw this graph. It looks like this. But over at 4, there's a hole in it. So this is actually the graph of x plus 4 over 2x minus 1, but with a hole in it. And that hole is at the value of 4. At the x value of 4. There's a hole in the graph, a single discontinuity where the graph is undefined at that one specific point. All right. I want you to take a moment, factor these next two, and figure out where the asymptotes are, and if there are any, find out where the point discontinuities are. I'm going to give you guys a few minutes to do that, and again, I'm going to count down, pause the video, work these out first, and then check your answer. If you made a mistake, just fix it. There's nothing wrong with that. All right, 3, 2, 1. All right, so I'm going to cover this really fast. You saw it. Okay. So all of these first two, the numerator and the denominator factor out using greatest common factor, and the x's cancel out. That causes a point discontinuity at 0, and everything else works like normal. And so we get this. Point discontinuity is at x equals 0, which causes a hole in the graph right on the y-axis. I should really add the x equals. At x equals 0. Alright, and it creates this swoop like this. For the second one, the numerator factors out using difference of squares into x minus 2 and x plus 2. The denominator stays x minus 2. That causes it to cancel out, which causes a point discontinuity at x equals 2. Now, real quick, because it's a quadratic over a linear, we know that the horizontal asymptote does not exist. But because there's nothing else in the denominator after these cancel out, it causes a vertical asymptote to be nowhere. And it causes this linear function because all that's left is x plus 2. So we get x plus 2, y equals x plus 2, with this hole in the middle at x equals 2. I am now going to move to RAT8. Alright, so just as a reminder, rational functions are functions that have a numerator function divided by a denominator function. And just as a recap of the rules, if the numerator function has a bigger degree than the denominator, then the horizontal asymptote does not exist. If the numerator has the same degree as the denominator, then you divide the leading coefficients, or divide leading coefficients. If the degree of the numerator is smaller than the degree of the denominator, then the horizontal asymptote is at y equals 0. And just as a recap, vertical asymptotes are wherever the denominator function is equal to 0. So wherever this function on the bottom is equal to 0, that causes an undefined, and that's what causes the vertical asymptote, unless it cancels out. If it cancels out, then wherever the denominator equals 0, and the numerator equals 0, that causes a point discontinuity, also known as a hole in the graph. And lastly, an x-intercept is wherever, this is new, an x-intercept is caused by the numerator equaling 0 uncancelled. So, looking at this first graph here, or looking at this first function here, x squared minus x minus 6 factors into x minus 3 and x plus 2. This is one of the examples that we did before in RAT6, but flipped over. It's the reciprocal. Okay, so horizontal asymptote. In this case, we have a quadratic over a linear. That horizontal asymptote does not exist. Vertical asymptote is wherever the denominator equals 0. That's going to be at x is not equal to negative 1, or x is equal to negative 1. This is where the vertical asymptote is. I'm going to rewrite that with the equal sign, not the not equal sign, because it's the equation of a vertical line. Up here, I'm going to write x is not equal to negative 1. There we go. Point discontinuities. In this case, the only thing in the denominator is that x plus 1. Nothing cancels, which causes no point discontinuities. And lastly, x-intercepts. The two x-intercepts in this case are where the numerator equals 0 and nothing cancels out. Because nothing cancels out, it's wherever this equals 0. So we've got x minus 3 and x plus 2, wherever these both equal 0. Well, that's going to be at positive 3 and negative 2. Positive 3 and negative 2. But because they're x-intercepts, we can write them as points. Now what we're going to do is I'm going to have you use Desmos Scientific to plug all of these x values into either the original equation or the factored form, which is, that. So you can either plug in these x values into the original equation, or you can plug them into the factored form. And whatever you get for f of x, that goes in this second column. Alright, I'm going to have you take about a minute. So just to do the first one for you, what I'm expecting you to do, in Desmos Scientific, you're going to take, I'm going to use the factored form. Alright, and you're going to take these x values and you're going to plug them in wherever x is. Again, we're using Desmos Scientific for this, not graphing, because graphing will ruin all of this. Alright, and from there, Desmos Scientific will also tell you that this is negative 3, and then you can use Desmos Scientific to do the rest of this table. Alright, if you want to do this on paper, use a separate sheet of paper. But I'm going to give you guys about 2 minutes to do the remaining 6 entries. Alright, 3, 2, 1. Alright, we should get these y values when we plug it in, when we plug in the x values. Now, this graph is actually a little bit messed up, so I apologize. Let me see if I can find a version where the graph is not messed up. Should have one over here. Maybe not. Okay. I'm going to keep searching, 1 second. Okay, I have fixed the graph to, I've kind of fixed the graph to show what it should look like on yours. The x-axis should be here, and this should not be the x-axis. Alright, anyway, the way that this should look, we're going to take all of these points on the table and we're going to plot them as points. So -3, -3 is our first point, for example. Again, this goes by 2's, so that's right here. Again, that is -3, -3. -3, -3. We should know how to plot points from a table, but I'm still going to go through it that one time anyway. Alright, and then from here you should be able to plot the rest of the points. Don't copy off of me. Use your table. As a matter of fact, I'm going to pause. I want you to copy, no, don't copy. I want you to plot the rest of these points on the table. Or I want you to plot the rest of these points from the table onto the graph. Also, one more thing before I pause. We have a vertical asymptote at -1, so I'm going to include that. That's actually very important. That's the reason why we have -1.5 and -0.5 here. It's because the vertical asymptote runs right through the middle of it. Okay, so I'm going to graph these real quick, and I will be right back. Okay, so unfortunately I messed up here because I forgot that this graph goes by 0.5s on the x-axis. So we now have this nice little swoop curve. Again, ignore this, that's not a point. Alright. And you'll also notice that there isn't actually a vertical asymptote. So this is actually still going up forever, and this is actually still going down forever, because there is no horizontal asymptote here, which makes sense. The horizontal asymptote doesn't exist. Alright, we're going to go over to the second one now. So I'm going to give you a few minutes to do this top part. 3, 2, 1. Alright, so just to go over this, the horizontal asymptote does not exist because we have a cubic over a quadratic. A cubic has a degree of 3, quadratic has a degree of 2. The degree of the numerator is bigger than the degree of the denominator, which means the horizontal asymptote does not exist. The vertical asymptote is at x equals -2 because none of these factors on the top, none of these x plus 1s, cancel with any of the x plus 2s. So the only thing that turns this denominator to 0 is x equals -2. So now we have this right here, this vertical asymptote right here. The point discontinuities don't exist because nothing cancels. And we have an x-intercept at -1, 0. Why? Because this numerator can only be set to 0 if x is -1. Alright, now you're going to do the same thing. You're going to plug these all into Desmos Scientific. And I'm going to give you guys a few minutes to do that before I show this. So 3, 2, 1. Okay, so this is what we should get. Yes, it is a lot of decimals, but we can still estimate where these points are on the graph. For example, -6 is the x value, -7.813. This is -20 here, so this is -5, -10, -15, -20. So -7.813 is going to be between -5 and -10, about halfway. That's about halfway there. Yep, about halfway between the two y lines, but right on -6. All right. You should be able to do all of these to the best of your ability. So what I want you to do is plot the remaining 6 points onto the graph, but don't connect the dots. 3, 2, 1. Alright, so here's what we get. Now, real quick, this point right here I drew a little bit too low. It should actually be very close to the x-axis. But you can see how, because there's the vertical asymptote here, we have some very weird shapes. Now this is the point where we actually go to Desmos graphing. So if you type in this into Desmos graphing, if you type this into Desmos graphing, it will actually give you the shape. And it gives you something like this. Alright, this is a very weird looking function, but this is what it looks like. So, because of this, you can tell that some irrational functions just are not able to be drawn just by looking at the points. Because of this, what I'm going to have you do on the back is plot the x-intercepts and the asymptotes, and then you're going to use Desmos graphing to do the rest. So on the back here, you're going to figure out the following information, and then you're going to plot the x-intercepts and the asymptotes by hand, and then you draw the shape using Desmos graphing and include the point discontinuities afterwards. Alright, that is all.